Okay, so now I'm going to take a tour of the machine learning APIs that Google has. And Google is really well known for the machine learning stuff on the back end. So it made sense if I was going to do any sort of API stuff, it would be their ML APIs. So here are some common applications that are consuming machine learning. There's optical character recognition to do language translation. You put up the camera, and then you go into translate, and then it will automatically do this in real time, translate the sign for you. Video recommendations, you can pull directly from their machine learning services based on the content of the actual video you're looking at. That's all done with that. Automatic image tagging, so if you have Google Photos and you put a search term in there, all that tagging is done with the Vision API. The autonomous vehicles is another one, and then the speech to text, basically the Alexa kind of functionality. This is all done with back-end machine learning APIs that Google has. And this is an enormous space. Machine learning is the huge buzzword now. And the problem is that machine learning that is being done right now is typically a very tiny subset of what machine learning is being used for in the broader context. And so if you take the AI and machine learning classes, you'll see the breadth of all the different kinds of systems that are classified as AI and machine learning. And so hopefully you do take these classes. Here are some examples. You have expert systems and decision trees. This is being used for medical diagnosis. So this is what the doctor is sitting here asking you a bunch of questions. You can automate the decision tree in the doctor's head using machine learning algorithms. And they've got, I guess IBM's Watson is better than your average physician in diagnosing based on the answers of the patient's answers. There's supervised learning. This is what happens when you do spam detection. You basically get a bunch of samples, and somebody sits there and labels things as spam or not. And the Bayesian filter can do conditional probabilities really well and be able to filter out one versus the other. Another one is unsupervised learning. So these are clustering algorithms where you take a bunch of the different inputs and then you try and group them together without any prior knowledge. You're doing similarity grouping of objects. So one of the things that it was initially used for that you might have used is Google News. How do I cluster articles without actually trying to do content analysis? How do I cluster articles that are all related to the same topic? And this is an unsupervised task that they want because they don't want people sitting there every single article that comes out to classify it. There are algorithms for combinatorial search. So chess and Go is the game that people are going after now with AI. Those are done more of as brute search optimization of the search space algorithm. Reinforcement learning, where it learns over time what moves will give it a reward. And so these are non-player characters in computer games in order to make them competitive to human players. And typically that helps the game experience for players. And then evolutionary and genetic algorithms, where you mutate an algorithm that you run and you check the performance over time. And if the performance if the performance improves for the particular algorithm that you chose, you use that as the candidate algorithm to breed with another algorithm to generate a more powerful algorithm. So this is like survival of the fittest when it comes to algorithms. And you'll see, so if you take the malware class, a lot of the smart fuzzing, smart fuzzing is a way of automatically detecting vulnerabilities in programs. A lot of those things are using genetic algorithms to try and figure out what is the best input to create a test case that will invoke a new code path, is the idea of their thing. And you'll see when we get to later on, there's an auto ML lab that I'm going to have you do. It's basically running a whole bunch of, so we did VirusTotal. VirusTotal takes 52 antivirus algorithms and runs them to see which one is best. AutoML is going to take maybe basically a dozen machine learning algorithms, and then run your model, run your data set on all dozen, and then figure out which one is best. So a similar idea of just throwing a bunch of algorithms out there, and then just selecting the best algorithm for your workload is another thing you can do. And these are all combined with each other, often combined with each other. But recently, everyone is talking about neural networks with supervised learning. And the thing that really kicked it off was actually getting a convolutional neural network to do a useful thing. And I'm going to go through a little bit of the history of this. So the neural networks approach models the way humans develop. And so this is a picture of the neuron density of a human from basically infancy all the way through 2 years. And the main thing that happens in your first 2 years is that you're building a whole bunch of neurons. And then as you learn over time, your brain starts to prune connections between all these neurons. So the neurons start fully connected, and then as it learns different things, it'll reinforce the things that it learns, and then a lot of the other connections start to disappear. And this is why language learning happens right around here, like being able to detect sounds, training your ear to detect certain sounds, being able to make certain sounds. As soon as you get beyond this, then those circuits are sort of not there for you to learn as quickly. Okay? And so this formula is what they are applying to almost all of the machine learning algorithms that are using neural networks. And so the idea is I start with a fully connected array of neurons, and then as I train and I learn different things, I get rewarded for certain outputs, I am going to change the weights of this, much like I'm pruning the neural network of a person's brain. So that's the idea. And so this has been around for a long time. So in the 1950s, this was proposed. And I had, like, on that Mac, from way back when I showed you that Mac, I had a neural network program. I was in high school, and I was like, sweet, neural networks on a floppy disk. And I put it in there, and it ran a neural network simulation. And so it was completely useless, though. I mean, it did some things, but it was nowhere near what we have now. So what happened? What happened was a whole lot of video game playing happened in the meantime, and people started generating these video cards with a massive number of processing units. Then the other thing that happened was people wanted to store a whole bunch of stuff, the internet, all of this multimedia content, and so the storage resources, the cost of storage went way down. And so now you have huge compute power, you have huge data storage, and this finally makes the approach feasible to learn something interesting. The last thing is that the internet gave us crowdsourced platforms that allow humans to label massive amounts of data. So I can basically crowdsource a library of images to the internet and pay people like half a penny per image classification, and then be able to get a training set that's pretty large. Okay, so this is what sort of revolutionized thing. It was ImageNet in 2009, where this really pioneered deep learning for image recognition for large corpuses of images. And the approach was to use these neural networks and to combine that with a massive amount of labeled data to solve the computer vision problem. And so neural networks came and went in the 90s, and then people stopped being interested in them. And so there was this PhD student who decided to try and revive it, and all of the academic skeptics at the time told her it wasn't possible. And so the approach that she took was to ignore all of them, to collect all the image data from the internet, and then to basically go to Amazon Mechanical Turk and get people to start labeling them, and then to send it through an enormous neural network. And then she definitely profited. But this is a talk that I would really recommend you listen to, because she took a huge academic risk. And she talks about how if this risk didn't pan out, she would have gone back to her parents' laundromat and started running that as a profession. So this is a really cool talk about how sometimes this kind of approach, proving your skeptics wrong, getting all this criticism, actually allowed her to go and do something cool. So now we have the ImageNet of all sorts of things. So people are grouping a whole bunch of data sets. So these are satellite images that they have created a data set for. A music data set, medical imaging is a huge thing for machine learning. This is what Watson is trying to do, like from a bunch of radiology images. Can I separate the ones that have an issue with the ones that don't? Normal versus diseased. You have different shapes, different events, different activities. But there is a big problem with this kind of approach that people often gloss over. The corpus itself has to be selected very carefully. And so there is an example early on with neural networks in the 1980s. So the military wants to be able to, with a neural network, decide whether that's an enemy tank or a friendly tank. So that was their initial application for neural networks, and it makes sense. The problem is that when you train the data set with the US tanks, you're going to be able to get pristine images because no tank manufacturer is going to give you an awful image of their tank. But all of the Russian tanks, you're getting from the field, right? And you're probably getting it from a plane 10,000 feet away from that tank. And so they're all grainy and fuzzy. And so they're like, okay, we're going to run a neural network. And it turns out what the neural network did was tell you the difference between a fuzzy image and a pristine image. So completely useless. But this is the problem, because if you don't consider what is going into your data set, you end up with these kinds of results. So hopefully Google isn't doing that with their stuff. So the famous line is garbage in and garbage out. That's basically an axiom of computer science as well. Another funny one is that they outsourced the labeling of vacation photos to Southeast Asian workers. So you're like, here's a corpus, label things as vacation settings and ones that aren't. And as it turns out, for a Southeast Asian worker who's maybe a fisherman, perhaps, they labeled these conference reception photos as being a vacation. Indoors, air-conditioned, in a business sort of convention center is their idea of a vacation. And it's probably because they're out there fishing all day long and they don't want to see a beach. So again, you have to think about how you're labeling, and Google is finally paying attention to this, and we'll see why they're paying attention to this. But this really matters. Yeah, and this is another question. What happens that this particular article raises? What happens when one uses these pristine photos taken by humans on high-quality cameras? What happens when you try and use those on drone applications that have very poor imaging? Like, what kind of results might you get? And this is where the engineering is going to have to happen. Okay, another big issue is bias in labeling. One of the big fears is that we're going to institutionalize bias behind this facade of an objective algorithm. People trust computers to be impartial, but if your data that you're using to train the data set is biased, you have just institutionalized it. You've just made it okay to say, oh, the computer decided it's not any bias that's already endemic. So this is a huge problem. And so you can encode racial and socioeconomic bias in your data set and then start discriminating against that data set. If you are interested in this area, there's this TED Talk that I highly recommend, and then this podcast from Google. So Google realized this was the famous thing that basically brought this to the forefront. Somebody tried to get the labels out of Google Photos, and Google Photos labeled this. You can't see it here. This has got a label of gorilla. And because they have not trained their data set with a diverse set of images, they end up having their classification algorithms do this kind of thing. They made the problem even worse, actually. Well, not worse, but they're trying to fix the problem. And the way they decided to fix the problem is to go to the homeless population and to try and convince them in exchange for like $5 to get their picture taken so that they can update their data set. But they were basically, I mean, they contracted it out to a third party people, but it looks bad when Google is sitting there paying to violate the privacy of homeless people to get their images into the data set. That happened a couple months ago, and then I don't know what they're doing with that. But this is something, at least they're trying to do the thing that's right, is to get data sets that are representative of the US population. But this is something that people should be thinking about. Okay. Another interesting one, machine learning for domestic violence. I want to do this. And people are pitching these things. It's like, yeah, I can do an automated detection. I can detect whether that person is a candidate for, or it would be a person who does domestic violence. And so the most common way for someone to have domestic violence reported is via complaint by a neighbor. And if you think about this, if you train a machine learning algorithm on the statistics of reports of domestic violence, what you'll end up measuring is learning that only people who live in row homes commit this crime, right? And so this, again, is something that you have to think about when you're doing this. Where they're right next, they share a shared wall. So it's not a single detached house where the sound would have to travel very far in order for you to get a report of these events happening. So yeah, that's what a row home is. Or an apartment building. And you say, oh, there's nobody in the rural areas that ever commit this crime because the data says so. And when in fact it's encoding something else on the back end. So these are all things that are interesting to explore. And then this is a quote from a machine learning, a famous machine learning person. It's not always so obvious ahead of time what the bad outcomes will be. You can't predict it a priori. And so we have, and I highly recommend you try and take a course from her, we have an expert in machine learning. She wrote this article that gets at a lot of these issues in the New York Times. That's the link to it. She just released this book, this awesome book on artificial intelligence, A Guide for Thinking Humans. That is something that if you have time to read, maybe after this class, you can read her book. Okay, another issue beyond bias are problematic cases that are very rare. So the machine learning algorithm can't learn anything unless it sees it, right? But if you never see a kangaroo jumping in front of your car, or if you never see a white semi-truck behind in front of a white cloud, then the machine learning doesn't know that, yes, that's a kangaroo. I don't need to, let's see, what did it do when it saw the kangaroo? I forget what it did. It did something nonsensical with the kangaroo, and then obviously the Tesla thought that this semi was a cloud, and then rammed right into it. So the problem here is that you have to train millions of miles in order to get those rare cases that you can then feed back into the machine learning algorithm. Now Tesla is getting this. They are getting all of this data, but it takes it a while to be able to learn all of this stuff. You also have to make sure you're training in the conditions that your machine learning algorithm is going to be used in. So again, rain, winter, spring, all of these different road conditions have to be tested before you start relying on this algorithm. Okay, another interesting problem is resistance to adversaries. So if you are, I teach the security classes. One of the things that you can do is, this is an example where they did a study where they trained a model to detect famous people's faces. And then this is one of the researchers, they basically created a set of eyeglasses that when this person put on, had him classified as her. Because of the way the math works. And it's the lack of understanding of what the bits underneath are doing that allows this to happen. The other one is in the upper right, you take a panda and you add some random noise to get this image, and what starts out as a panda ends up as a gibbon, when it's clearly not a gibbon. Gibbon is like a monkey, yeah.
Also the juggalos, like insane clown classification, also protects you from because you can't do the angles to
Yep. The other, so, and then on the bottom right, you see these nonsensical images. These can get classified as these items, right? Because there is no underlying common sense that's being done in the bottom. There's no actually higher level features being pulled out of this. It's just a bunch of math, opaque math settings on the back end. Okay, another issue is that it requires large-scale participation in data. And so this is a picture of the number of entries in your data set and the impact that those entries have on the recall or the precision and the errors in your classifier. So you need a huge data set over here in order to get 2/3 accuracy, precision on this task. And so you need a lot of data. And so this was a quote of one of these machine learning researchers. They make the claim that data sets and not the algorithms are the key limiting factor, right? Because now the algorithms everyone knows. But now, in order to get the thing accurate, you actually need a large amount of data. So there's a race to collect data in order to make the machine learning work best. And this is where Kaggle comes in. They decided to spin out the data sets for ImageNet into this open source repository called Kaggle. And so this is a community-based machine learning platform that a lot of data scientists and machine learning engineers are using. And so there's a huge number of data sets that you can pull out of Kaggle. This hosted data sets are, this is out of date, but it's several thousand now. And then everyone is using this to train all of their data. The question I'm going to ask is, who on this planet has the largest, most interesting data sets? Yeah, Google. So this is why their machine, this is the strategy that they're using to monetize their services. They have data that nobody else has, and so they can build ML data products better than anyone else out there. And so they're basically monetizing their data. And this is why they would acquire something like VirusTotal to get the malware samples. This is why you would acquire like a YouTube or a Waze to get all the data from people effectively. Okay. So this is software's new application building block, right? So now we talked about the Windows SDK. This is what the Cloud SDK is looking at. You are integrating all of these different services into your app and leveraging what Google has done and what other people have done. Okay, so why build your own machine learning models when you can have a Translate API, you can have a video intelligence one, a Cloud Vision, you can do all of these things with a REST API, basically. So all of these things are accessible via REST. They're also accessible via Python packages in Google. And that's what all your labs will be doing this. How do I integrate my Python and how do I integrate REST APIs to pull all of this information out of their backend? Okay, so the first one we're going to use is Cloud Vision. You give Cloud Vision an image and it will figure out what it is. So that's the image labeling. It will figure out if you give it a face, it will try and cluster the face to identify who it is if you have a bunch of labeled people. It will give you sentiment analysis. Are the people happy or unhappy in this photo? It will turn any pictures of signs in your image, and it'll do the text detection. So it'll do the OCR operation in this API. You already did this one, the safe search content identification. This was your Cloud Function one, where the trigger would do the detection of adult or violent content. You can identify corporate logos as part of this API, and then very popular, well-known landmarks. So like the Eiffel Tower will be identified with this API. The other one you're going to use is the speech API, and this is speech to text. So word recognition, transcription, automated punctuation, and then offensive content detection, as well as, this will be in the Translate, the sentiment analysis. You can also do speech synthesis. There have been some projects where they use this to get your website to talk to you. That's a project you could do, and this is all done in a whole bunch of languages. There's the translation API, so language detection and translation in 100 different languages, and then they have all the bindings to access it. Natural language API, so this is syntax analysis of what's being given to it, semantic analysis of the meaning of what's being given to it, and then sentiment analysis. And this is the API that they're using. If you see the auto-completion of emails, this is what they're using to predict that kind of stuff. The other one is the Cloud Video Intelligence API. You give it a video, and it will go through the video and basically annotate the video with everything that it sees. And what it'll do is you can get a JSON back that says, oh, these are the particular parts of this clip that have baseball associated with it. So it'll automatically do the image recognition on your clips and then allow you to label the different parts of the video that show baseball being played. Okay. Let's see here. So there is a demo. So if you remember the image transcoding lab that you did, this person made an equivalent lab that I'm not going to have you do, but an equivalent lab for doing the exact same thing using video intelligence, where you upload a video, and then this triggers a cloud function to run the video through the video intelligence API, and that spits out metadata about that video. Is this particular demo? I think this is a link if you want to see this running. Okay, the last part of this is ML as a service. So one of the things is it's really hard to find machine learning engineers out there. And so if you're a company and you want to build a machine learning model specific for your use, so I am an auto parts manufacturer, and I want to build an ML image recognition algorithm that identifies auto parts, I don't want to hire a six-figure machine learning person to do that. And so what a lot of these cloud providers are doing is these hosted machine learning services that allow you to generate your own machine learning model without having to understand the underlying thing. And so this is what I mentioned earlier with the 13 different ML models that you just pick the best one for. That's what this service is doing. What I am going to have you do is to do the Auto ML lab of this thing, which does this. So Cloud Auto ML for vision. The idea here is that the Cloud Vision data set has been trained on all of the images that Google has. But if you have a corpus that is all machine parts and you want to use that to train another model, what you can do is something called transfer learning. You can take the Google machine learning model for regular images and then just update it with the images that you have labeled for machine parts. And that's what the AutoML service is doing. And so you basically you give Google a bunch of image data that's labeled, or you can give it unlabeled data, and then they can do the mechanical Turk operation to have humans do the labeling. And then it will emit, after this, a custom model that enables you to use machine learning specific for your domain. So for this, the lab that you're going to do is to classify clouds, different types of clouds, using the Google Vision API, using the AutoML API. Okay. And this is so this is Fei-Fei Li's big thing. She wants to democratize machine learning for the masses, so that you don't necessarily have to know the underlying mechanics of the neural networks in order to build an application that uses machine learning. And that's what this product is meant to do. So I wanted you to see it just in case, so that you know that it's actually out there for use. Okay, so this is a great example. This is an article on using this AutoML to identify different ramen shops. So like based on the arrangement of the ramen dish, you can specify which restaurant. And of course, the regular image set only shows ramen as the label, but here you want to actually create a new one that drills down to the actual ramen shop that has that particular dish. So that's an application that if you click on that link, you can read about. I'm gonna skip that. So I wanted to give you sort of an overview of how these things are all put together. Similar to the other, like something like the Super Mario Run. How do you build an end-to-end application using all of this stuff? And the application that I'm going to walk you through is this Envato. I don't know how to pronounce that. And this is basically YouTube infrastructure as a service. Like if you're a company and you want to build a bunch of things that are very similar to YouTube, this particular company is allowing you to do that. It's wrapping around all that functionality and allowing you to deploy something similar. So this is what it looks like. Up at the top, if you have a live event that you're basically trying to capture and distribute to all of your users, then what you have is an encoding operation, and then you want to stream this to some video server. And so when you get it to this video server, if you're trying to broadcast this, one of the things that you'll want to do is closed captioning on that video stream. So in real time, you can call into the speech API for the transcription, and then you can do the translate API to get all of the different languages to close caption onto. So this is the first step. Then what you might want is to transcode that video to all of the different resolutions. So single definition, high definition, mobile, those can get all transcoded here, and then you could use something like compute engines to do the transcoding operation. And then obviously you're going to store this stuff in cloud storage, the intermediate results. The next thing you might do is insert ads. And then for ad insertion, you might be running video intelligence to figure out the context of what the video is doing. And then you can target an ad based on the context of the video that you're getting. And then you would also call into AdSense, right? Based on a keyword that video intelligence is giving me, I can then advertise. I can go into the ad network and say, hey, a picture of a car is being shown. Who wants to bid to get an imprint of an ad in the video? And this is like this real-time bidding for ads. That's what AdSense is doing. And then there's a marketplace for ads being shown. And then this would basically tap into that. You could also do object detection with vision if you wanted to use that as input to AdSense, or natural language. So what are they talking about in this video clip? And that could be used in your AdSense input. And then finally, distribution to global users. So all of the CDN operations that YouTube has, you could then ship out. And so this is what Univision is who this is? This is what Univision is doing. This is one of these TV channels that's trying to build a streaming service. Okay. Here's another example of putting all these APIs together. New York Times has this huge corpus of photos, and it wants to be able to index them and search them for its users. And so this is what they did. They digitized all of their photos. They have archival photos. That gets put into cloud storage. From cloud storage, you want to hit, this does the trigger for a cloud function to process these images. And that's done through PubSub. And then they transcode the image into multiple resolutions. And that's done with a compute service. And then they run these things, they store those things back in cloud storage, and then they run these things through the Vision API to get the labels so that they can then build an index that allows it to be searched. And this is what images.google.com is doing. It's got all of this recognition stuff, and then they're indexing based on the objects that it detects in the image. And then you can store any of this, all of the indices and the metadata in a database backend, and they chose Cloud SQL for this. So this is another one. If you go, there's a link here that you can click on to see how they've done this. Okay, and so with that, I am going to, I don't have time to do all of the ML APIs. What I want to do is I want to cover the one that really matters. And the one that matters is the integration of the ML APIs with a Python Flask app. So that's what I'm going to cover now. Let me see. Okay, so one of the things about this lab is that you have to make sure you do ML API lab number 1 first. Because in ML API lab number 1, I walk you through how do you get your credentials to enable access to the ML APIs. So you're going to have to enable all of the ML APIs for your project so that it can charge your account. And then what you need to do is you need to generate a credential that allows you access to the ML APIs in order for all this stuff to work. And so that is shown in the first lab. So make sure that you've done that before you do any of these things. This is why I say skip these steps, because I'm assuming you've done ML API lab number 1. The actual code is in the repository that you have cloned already. So Flex and Vision. This is App Engine Flex using the Vision API. So again, we're going to reuse the service account that we created in the first lab and then point the credentials to allow access to the APIs. And then this is the command. So you're giving it a role to allow you access to change the subscriptions of your service account. And this is how you run the app. You create a virtual environment, you source it, you install the packages, basically the cloud storage and the cloud vision. And then in environment variables, you specify the storage bucket, because you need a storage bucket to store the images that you're going to upload to then do the machine learning operation on. And so you need to make sure you have a storage bucket that has your project ID as the name, is the thing that it's looking for. And then you can just do a gcloud app deploy just to see that this app works. And what this app does is that when you preview this app, so if you do a regular, if you use the dev app server, then you can preview this on 8080. If you do the deploy, then you can actually go to the endpoint that gcloud app deploy gives you, and then you'll get something that looks like this, where it asks you to upload a file, and then basically based on the file you upload, it measures your likelihood of expressing joy in this image. And it's using the Cloud Vision API to get sentiment analysis on faces. So there's a face detection part of the Cloud Vision, and it's using that to figure out that, yes, this is someone who's happy. So this is the code for accessing the Cloud Vision API to get this thing done. So it has a single route / that returns a home page. It's going to create, so when you do the annotation, it's going to store the result in data store. So that's what this thing does. It creates a data store client, and it gives you a new kind called faces. So hopefully your app isn't using the face kind. I don't know why it's using bubble tea. So they should be separate. And then it's saying create a new kind called faces. And then what I'm going to do is I'm going to so in data store, I might have previous image detections in data store that I've uploaded previously. This is just going to get all of the entries I've already classified and then dump them out into the home page is the second thing. So that's my basic, the home page is effectively what that is. And then this is the route for uploading a photo. So if I click on upload photo, which is the link that home page will serve up, then this is what the route will do. If you click on the form and it says choose file and you say this is the path to my file, then that is pulled from the request by Flask. Flask will then create a storage client, because what you're going to do is this thing is going to get uploaded, and then from this route you're going to store the image into this bucket. So this is the way of programmatically getting that bucket, and then you're going to pull you're going to create a blob that's got this photo in it, and then you're going to call this upload from string, and you're going to read the photo, and then you're going to make it public, and then this basically stores this photo into cloud storage. Okay, and then you can pull the link out of it in a later step. So this blob now has your photo stored in cloud storage. And then you create a Vision client. So this is the API for Vision. So from google.cloud, you import this Vision object. And the Vision client is you pull from the Vision package this annotator client. So there are multiple parts of the Vision API. I'm only interested in the annotation that is labeling whether or not someone is joyful or not. and that's what the image annotator client does. And then I'm going to point, I'm going to create this URI to say which image do I want Vision to process, and that's basically what this is. I'm going to give it the blob name that I just uploaded and say it's from gs:// my storage bucket with this blob name. And then I'm going to create an image using this image type from the Vision API and give it this source. And I'm going to point that to this URL. So this creates the image object for the Vision API. And then I'm going to say, I'm going to call the Vision client to do a face detection on this image, and then to pull out the face annotations. And this is the JSON thing that gets pulled back. It's going to give me a JSON object that I can then parse to figure out what the results are. And this is what this code is doing. So it's pulling out the results from the annotation, and it's pulling out the joy likelihood, which is face.joy likelihood, and it's one of these values. And then it stores that. It stores this in data store. So this is the data store client. It records when it did this thing. It specifies the kind. It specifies the URI of the actual image. And then it stores both of those things into the backend so that it can be rendered the next time around. And then that's, it keeps all of that and then it puts it into the data store backend. Okay? And then it redirects you to the home page. So that's the entire app. And so from that, you can see how you import the Google Cloud packages, and then you can use it to actually build your application. This is what your final project is going to be. And so your final project, how much time do I have? Oh, I have some time. So I put this as a PDF in the Google Drive. And of course, I can't see anything here. How did that work? So for the final project, I am going to allow you to work in pairs if you would like. But the requirements are, for graduate students, a minimum of 2 API integrations per student for a passing grade, and then for undergraduates, at least 1 API integration per student must be implemented for a passing grade. So if you're undergraduates and you're working together, you need at least 2 API integrations. And those are integrations of your choice. You can go and be creative. So the integration, having an integration gets you a passing grade, but it's the level, the functionality that you're using in the integration that will also be graded. So the more functional the integration is, the higher the grade is going to be. But you can take any of the APIs that we just talked about, the vision, text-to-speech, natural language processing, any of the external ones, any ones that you want to integrate into your app that you know of from Rapid APIs, for example. Figure out some kind of APIs that you want to use in your web app, and then just integrate it into your Python App Engine application. Submission of this. There are 3 parts to this submission. The first part is the code submission and URL posting. So this is going to be Tuesday of finals week is the code submission. And then the code is going to be zipped. So it's going to be, you have to commit this in your Bitbucket repository. And then in D2L as a zipped folder. And then in your repository, you need this final/url.txt that gives us the URL to hit your app. And this app should be left running. And we're expecting this app to be an App Engine running. The other thing is after you have submitted your code and your URL to Bitbucket, I want you to visit my guestbook and submit your URL there, because Wednesday of finals week, during our final exam slot, that's when the demos are going to be. And so what we'll have you do is just come up for maybe 1 or 2 minutes and just show your app off. And then, so that will be Wednesday. Then what we want you to do, so Wednesday finals is 12:30 to 2:20. That's what this part is. It's a 1 to 2 minute demo. And obviously if you've done it in pairs and you have more functionality to show off, it'll be 2 to 4 minutes. And then at the end of finals week, we're going to have you do a narrated screencast where you basically go through all of the steps in your project, the source code. You're going to describe what you have implemented. So if you've done it in pairs, we want each partner to describe the part that they implemented. And this will allow us to assign group work. So who has done what? And this will be done with the screencast. And I will I should have it so that I've added people to a channel, and I'll point you to where the screencast is going to go. Okay. So this is the rubric. This is now as a PDF in that Google Drive folder. If you have any questions about what is being asked of you, let us know. So with that, I think I'm going to end here. Are there any questions about what you're going to be doing? All right.